Okay, okay, okay. So now we are definitely going to continue with this topic of momentum and impulse. So without wasting much of our precious time, I will definitely start from there. You say now we are going to be talking about Newton's chain, whereby here they are saying Newton's second law in terms of momentum. Okay, we're talking about Newton's second law, but in terms of momentum. Okay, so the resultant or net force, very much important. The resultant or net force, which is acting on an object, they say it is equal, most importantly, to the rate of change of momentum of the net force. Okay, yeah, too much of English there. But what I remember is that when it comes to physical sciences, sometimes they give a definition which does not instantly click. But trust me when I say, the more you engage with the formulas, the calculation, the problems, and all of that, that's when things start to make some nicer sense. So just be aware of that honorable member or the member who is honorable. Okay, so now let's see. They are talking about Newton's second law in terms of momentum, which is the resultant or net force acting on an object. Okay, it's a force acting on an object. And they say that is actually equals to the rate of change of momentum. What I know is that the rate is something over time. Something over time. What is that something? It is change of momentum. Okay, then it's fine. And in the direct, okay. So according to Newton's second law, a resultant force applied to an object will cause the object to accelerate. Okay, when the net force on an object changes, so does its velocity and hence the momentum. Yes, so the velocity will have a greater influence on the momentum because the mass stays the same. The mass of an object stays the same, but the more there is a force acting on that object, it will influence its velocity. Then the change in its velocity will therefore influence the momentum of that object. But maybe let me just show you what's happening there based on Newton's second law, just so that we can end up with that formula. I think out of this, that part is the most important one. The rest will definitely start making sense as we continue. I'm not sure if you remember, honorable member, but what we know is that F net, the net force or the resultant force, equals to MA. I'm sure you do remember this formula by now, honorable member, whereby I'm not sure the acceleration, I'm not sure if you remember, but acceleration, it's equals to V final minus V initial divided by time. That we know most. So it therefore means F net is therefore equals to the mass. Inside the brackets, we're going to have our formula for the acceleration, which is that over change in time. So if we have to now simplify this thing, maybe if you want to be reminded, they would say acceleration equals to change in velocity over change in time, whereby change in velocity, we know change means V final minus V initial. So that's what I'm having there. Then as we continue with this thing, which will therefore say F net will be equals to, can we not do that by that, where we say we have MV final minus MV initial over a change in time. I think you would agree with me on that one, honorable member. And when you look at this thing nicely, you will actually realize that The numerator now, wait, I'm glad that I'm actually tracking if my thing is sharing. So now my screen is disappearing now, this way, because with some other recordings, the screen would just disappear in the background. And from there, I wouldn't know if it has disappeared that nature. Okay, so let's see. Let me just wait for it to share the screen, and then once it has done that, then I will know that I am ready to go. It looks like I'm ready to go. Okay. So you see there, it says Fnet, it is equals to MV final minus MV initial. And that part alone is the same as what we discussed on the previous lesson where we said it is change in momentum because we have MV final minus MV initial. So that means this thing is the same as change in momentum over a change in time, isn't it? And trust me, when I therefore say this formula can therefore be simplified as, so just make it flat and don't have those, excuse me, the fraction thing. So that means we will then cross multiply by that. We end up having a net where we multiply change in time, which is therefore equals to change in momentum. And this is where that formula it is coming from, whereby obviously the F net, F is a force mass, so it will always be multiplied, measured in newtons. And then the time, I think it's easier, we know in physics is measured in seconds. And then that one is the momentum, it doesn't change, will always be measured in meters, kilograms, meters per second. Yes. So that's what we are having. It comes from deriving that formula of net equals MA. Yes. Okay. So now let us continue to this other part. What are they talking about there, Honorable? Okay, here they are talking about an impulse. What is the impulse? Wait, did my screen disappear again? It looks like because I'm not able to see it on this other side. Let me go back and why does it disappear unacted? Could it be the network? Who knows? Okay, let me share again. And let me share again. I'm glad that I was able to pick it up. Okay, still saving the image. Okay, I'll just wait for it to save. Then from there, let's see. I don't know why it's taking this long to save an image, but it's fine. Just wait for it to save. Okay, so impulse, what is being the product of the net force acting on an object and the time the what is the time over which the net force acts on an object? Yes, this should definitely be the definition of an impulse. So that means when it comes to an impulse, we are talking about the product of the force and the time. That's it in short, honorable member. Product of the force and time. So product of the force and time, that is the impulse. So in other words, impulse is the same as force multiplied by time. That's it. That's it, honorable. So by rearranging Newton's second law in terms of momentum, we find that impulse is equal to the change in momentum of an object according to the impulse momentum theorem. Yes, I think this one, they are just talking about the formula. If you can listen very carefully, you will realize that impulse is indeed equal to the change in momentum. Because if impulse, it is the same as F times time, what is that equals to? It is equals to change in momentum. So that's what they are saying there to say impulse is equals to change in momentum. Obviously, Ft and Ft is the same as change in momentum. That's why you see that. And then here, they are talking about the mass multiplying change in V. That is change in momentum, because if you don't understand that part, it's like having mass V final minus mass V initial. The mass is the same mass. So that's why that mass gets to be taken out as a common factor, and then you remain with V final minus V initial. What is something final minus something initial? It's a change. So that is why you end up having that in V. That is where that formula is coming from, which is equals to change in momentum. So just make sure to never be confused, honorable member. I think I am definitely making it easy for you to understand there to say a more impulse, which is equals to a force times time. It is therefore measured in ns. Why ns? Because n for the Newton and then s for the time. So I hope that part makes sense. And again, if it is the change in momentum that you are calculating, then you will represent it in that way. So that is clear that when you say ns, we know the question wanted you to calculate the impulse. When you say kilograms meters per second, we know the question wanted you to calculate change in momentum. So I hope that part, honorable member, it makes sense. I would like to believe that that part makes sense. So now let's continue. This is where I am now, where they're talking about the change in momentum. They are saying the change. They are saying the change in momentum is directly dependent on the magnitude of the resultant force and the duration for which the force is applied. Impulse is a vector. Okay, therefore it has a direction. And the impulse is a vector, just like momentum is a vector quantity. Impulse is also a vector quantity. That one is clear. That means it has the magnitude and the direction. So now they're talking about the change in momentum is directly dependent on the magnitude of the resultant force and duration for which. Okay, that part is fine. They are still emphasizing what you already understand by that, the formula to say the change in momentum, which is this thing, that is the change in momentum. So it is definitely dependent on the magnitude of the resultant force. It is dependent on the force and also the time. So in other words, they're talking about momentum being dependent on the force and the time. Anything else is just to make that English make sense, honorable member. Okay, for me, I've realized over the time that actually physical sciences, it made sense when I started doing the calculations. Not, I firstly focus on the calculations themselves, and not just do it once, honorable members, many times. Many times as you can, you need to redo those calculations, do them. Try find some more examples to work on, do those, and then somehow in reverse, the theory part will therefore make sense. So that is why I'll also work towards gathering as many problems as I can related to these calculations of momentum and all of that, so that at least you can practice enough. Okay. So now let's see. Here is an example that we can have a look at. where they are talking about a golf ball with a mass of 0.1 kg is driven from the tee. Okay, the golf ball experiences a force of 1000 Newton while in contact with the golf club. Okay, and moves away from the golf club at 30 meters per second. Okay, so for how long was the golf club in contact with the ball? So can you see, we are talking about something that has to do with momentum and all of that. The moment force is involved, think of that formula of net force of force net times time equals to change in momentum. Always remember that formula where you are dealing with momentum and all of a sudden there's Newton involved. So you can see now that, okay, the force net, it was given to us as 1000, isn't it? That's why we substituted it there. And then with regards to the mass, it is that one of 0.5 because that mass doesn't change. So it's like it was taken out as a common factor from that formula of mv final minus mv initial. The mass, it is still the same mass, was taken out as a common factor. So now let's see, a golf ball with mass of 0, that is driven from the tee. Okay, the golf ball experiences a force of 1000 Newton while in contact with the golf club and moves away from the golf club as at 30 meters per second. Okay, so now they are asking for how long was the golf club in contact with the ball. Okay, I think it now makes sense. So obviously after substituting that mass of 0.5, maybe let me expand this formula to say it's m v final minus v initial. So initially the ball was at rest, nay, and then it was driven from the tee until what happens? Until whereby it moves away from the golf club at 30 meters per second. Okay, so now that means the final velocity, it is that one of 30 meters per second. Yes. And then now all that you need to do, it is to work out the whole of this. You will definitely divide it by 1000. Once you've done that, this is the answer that you get. You may find that this thing may be 0.003 seconds. Yes, something of that nature, honorable member. And that becomes your final answer in seconds, because it is the time that they wanted you to calculate how long. So when they say how long, indirectly they want you to calculate the time. So okay, here's another example that you can think of. They are saying, why can airbags be useful during a collision? No airbag moves inside the car. So they say, state your answer by using the relevant scientific principle. So here, in answering this question, they are making use of the momentum to say the change in momentum remains constant, but the use of an airbag prolongs the time of impact during the accident. So the resultant force experienced is inversely proportional to the contact time, therefore resulting in a smaller resultant force, that is changing momentum is constant. Okay, maybe let me try explain this using the formula, honorable member. This is what happens, honorable. Remember, the force equals to change in momentum over change in time. Yes. So in other words, they are simply saying this one, it remains constant that's what they said, or it's conserved. Let me quickly verify. The change in momentum remains constant. Yes, this is that part there. And then you can see that part over there. I'll explain it just now. So since that one, it remains constant, we therefore remove it and say the force net, we are actually having that being indirectly proportional to the inversely proportional to the change in time. So it's like, think of it this way, honorable member. If this is the seat, and then this is that steering wheel in the car, something of that nature. And then this is you now, you are seated there on the car, and those are your hands you are driving. Okay, so during the impact, during the accident, what we are trying to do when they talk about that time there, they are simply saying, once that bag blows, the more it takes longer for you to be in contact with that steering, the lesser the force. The lesser the force. So imagine someone is calling. I hope it won't disturb my recording. I'll just end that. Okay. So imagine a situation whereby it takes long for you to be in contact with that steering wheel. You won't feel much of a pain as you compare with a situation where there is no airbag. Immediately after the accident, same time, you just move that steering. So that is the principle that you say, the longer it takes, the longer it takes, the lesser the force. That is why that thing is F, it's inversely proportional to the time. If something is directly proportional to the time, it would be like this, whereby the longer it takes, the more the pain. But this one, the longer it takes, the less the pain. Yes, something of that nature, honorable member. I think as we do some more examples on that one, it will therefore make some sense. So here, the last example they are talking about, the following graph that shows the force exerted on a hockey ball over time. Okay, the hockey ball initially stationary and has a mass of 150 grams. Okay, so you can see there, it is the time where initially it was that, then we have that, and that being the force, and then it forms that shape over there. Okay, now they want you to calculate the magnitude of the impulse, being the change in momentum of the hockey ball. Okay, then it's fine. So here, what we know is that in a situation where force is involved and then time is involved, we will definitely remember this formula, which says F net equals not F net, but just not just F net, but F net multiplied by time. It is the one that equals to the impulse. So, but this one is calculated differently, whereby it's that form of a graph, whereby what you're going to do there, you will therefore say this impulse is equals to that area under the graph. So all that you need to do is just to calculate the area for that graph. That's how you work it out or deal with it decisively. So how do you do that? It is half that you multiply by the breadth and the perpendicular height. So half, because you can see this thing is a triangle. So that's why the formula is half there. And then the breadth 0,5, which is that side there. From 0 to there, it's 0,5. And then you multiply it by the perpendicular height being that one there, which is 150. And then that calculation itself, it therefore gives you that 37.8 5 Newton second. And that's how you would calculate your impulse. Okay, so this section of it looks like it's a bit of a tricky one, but trust me when I say the more you do some more examples, that's when it's going to make sense. I will try, see if I can be able to find or derive some questions that you can use as a practice. So on our next lesson, we will therefore be looking at a conservation of momentum, where we look at different types of collisions and also explosions. Then from there, once this part is done, we should be ready to get started with some exam type of questions, where we look at how questions are asked, how you are expected to answer those questions. Okay, I think I'll leave it here and say until we meet. Okay. Until we meet. Okay.